Hey, good morning, everybody. Hey, welcome to Papa Lim Physics Classroom. Okay, today we will be going through one of the assessment paper that I gave for my student. Okay, the paper, if you need the paper, is in the description below. I put a link there to my Google Drive. Okay, feel free to download and try out yourself. For the answers, right, later I'll be going through. It's going to be a long video. Okay, if you need like a particular question, just forward to that particular section that you need, okay, so that you can get the necessary informations or feedback on that particular question. Okay, without delaying, okay, here we go. Okay, good morning, everybody. Welcome to Papa Lim Physics Classroom. Okay, today we will run through the 2022 mid-year paper. Okay, particularly paper 1 and paper 2 for science physics. Okay, for my students who are watching the video, okay, if you need like certain questions or you need certain part of like paper 2, okay, remember to just scroll to the correct section and just take a look at what you need. Okay, don't look at the whole paper, the whole video, because it's going to be very, very long, maybe an hour plus. Okay, so just get what you need. After that, focus on, remember, not focus on the answer. Okay, focus on the thinking process of how I get the answer, how I solve it. Okay, thinking process is more important than actually the answer itself. Okay, so without delaying, okay, let's look at the paper itself. Okay, now the 2022 mid-year paper, paper 1 first. Okay, we'll look at paper 1, the MCQ paper. Okay, so those who have not got the answers, okay, I flash the answer here. You can pause your video while you copy down answer or check your answers. Now, for paper 1, I would say some of the questions are interesting. Okay, overall, the paper, I will classify paper 1 as I would say it's an average paper. Okay, some are quite easy, some are like slightly tricky. Okay, for example, question 2. Okay, question 2 wise, okay, important thing is we are looking at it as a throw-out object is a free fall, where the stone is being thrown vertically upwards, and the question asks for the characteristics of the stone when it is at maximum height. So now for students, right, you must be careful when we talk about maximum height. There are a few characteristics that is pegged to this particular position. For example, right, if I have a stone at maximum height, yeah, throw all the way up. Now at maximum height, of course, the obvious one will be like the height will be the maximum. The height here is max. Okay, then at maximum height, you will find that is under the only influence that it has at this moment is under the influence of gravity, gravitational field strength, your attraction pull. So the acceleration that is actually experienced at this point in time is actually the gravitational field strength, the pull of the Earth, which is actually 10 meters per second square. And at the highest position, the ball will actually stay like momentarily stop for a while, okay, because all the speed will reset back to 0, and as a result, okay, it will stay in the air for like a very, very small timing, a millisecond. After that, it will start to come down again. So for object that is thrown vertically upwards, there are 3 characteristics that you have to know. Okay, for example, at maximum height, at the highest position, the height is actually the highest, and actually the speed is actually the slowest, or in fact, it's actually 0 meters per second. And the gravitational field strength will be the acceleration it will be experienced is what we call acceleration due to free fall, which is 10 meters per second square. So with this in mind, you will know that the answer actually for question 2 will be actually C. Okay, and same thing if you look at this question, right, on the reverse, right, if I don't look at maximum height, so what I do now is I look at it as let's say I look at it as a minimum, the lowest point. So when the object is being thrown and is at the lowest point, okay, there are certain characteristics that you have to know. Okay, at the lowest point, okay, I will know that the height it experienced will have to be the minimum. Okay, whether it's 0 or not, it depends on the question, but I do know that height will be the minimum at the lowest height. And at the lowest point, okay, other than height is at the lowest, I also know a few things. I will know that the velocity at this particular point, at the lowest point, will be actually what we call the maximum, okay, which is all the kinetic potential and gravitational potential energy are converted to kinetic energy. So for object that is at the lowest height, where you'll find that the height will be the minimum and the velocity on the other hand will be actually the maximum. So we will talk about object at maximum height or object at lowest height or lowest point. There are certain characteristics of certain specification that you have actually need to know. okay, as a student, okay, if you want to look at it for your physics question. Vernier caliper, micrometer, screw gauge. I will not dwell too much into it, but I just need to remind the students to actually look at how we read vernier caliper and micrometer, screw gauge. Okay, please know how to read them and judge and get your answer accordingly. Now, for question 4, okay, question 4 is a very classic example of like a pushing box or Newton's law question, whereby you have a box, okay, which is 50 kg. Okay, this is the 50 kg mass. Okay, make sure the unit is in SI unit, kg. It's being pushed with a force of 340. Then after that, the total friction force they give you, friction force is opposing. So the friction force will be opposing between the surfaces. It will be actually 320. Now here, take note, okay, a reminder for students, okay, when you look at frictional force, remember how you draw your frictional force, okay? How do I erase this? Okay, your frictional force, okay, you have to be drawn at the surface, okay, the surface of the thing, okay, make sure it is always at the, be in between the surfaces. Okay, so now you have two forces acting on the object, and the mass is 50 kg, so you want to find the acceleration, so you'll be a classic example of Newton's law, F net, okay, equal to ma. F net, you'll be the applied force, which is 340 minus 320. Mass will be 50 kg. Take note, a booby trap, please make sure it is in kg, SI unit, followed by acceleration. So if you do the math, you'll know that acceleration will be 20 equal to 58. After that, you solve for A. You do a simple algebra here, you will get an answer to be A, 0.4. Okay, so I would say it's a simple question now, so you shouldn't be taking too much time. Remember, for MCQ, okay, simple question, easy question, you try to solve it so that you can save the extra time you have for that particular question for other questions at the later part of the story, okay, of the paper itself. Okay, for paper 5, question 5, okay, if it's traveling at constant speed, okay, over a large patch of oil, and if I'm to apply a brake to stop the car, large patch of oil means this guy is what we call slippery. Okay, so which means your friction will actually be reduced. Okay, so compared to a dry road, okay, because it's slippery now, so definitely your brakes will be like weaker, the friction will be smaller. Okay, so as a result, what you get is actually your friction force will be reduced, and because of that, your car will actually travel a longer distance before it slow down. Okay, so I would say this question, students, you have to actually read carefully because it's quite a lengthy story. Okay, so please read carefully. Now, number 6 is quite easy. I will skip that. It's a typical formula of weight equal to mg. Now, for number 7, again, 7 is a classic example of moments, principle of moments. Okay, so when we talk about the size of the pivot that's needed, and the question mentioned about pivot, so we are looking at a turning effect question. So for the force 600 Newton, the perpendicular distance I'm looking at is actually here from the pivot to the force, which is 70 cm. Okay, so for 600 Newton, it will be a clockwise moment. Okay, perpendicular distance will be 70 cm, force will be 600 Newton. For the force applied, okay, by basically the person to lift, okay, you'll be here. This is the force I'm looking at. Okay, remember, the point to take note is I'm given 50 cm, but this is not the perpendicular distance I want. Perpendicular distance is always measured from the pivot all the way to the force himself. Okay, so the perpendicular distance for force is actually 70 plus 50 cm. Okay, and this will be an anti-clockwise moment. So once you have all the necessary moments, so what you do is a standard approach. Anti-clockwise moment equal to clockwise moment. Okay, clockwise moment is the red color one, which is 600 multiplied by 70 cm. Then followed by the anti-clockwise moment, which is F, multiplied by the perpendicular distance. Remember, it's 70 plus 50. Yeah, so now the 70 plus 50 cm, okay, so will be 130. Oh, sorry, 120 cm. Okay, so this will be 120 cm, followed by 600 multiplied by 700. So you do a simple 70 cm, sorry, not 700. What am I doing then? Okay, so it will be 70 cm. So if you look at the math, okay, you will solve for F, and you'll find that The F will be actually 350, no. F will be question 7. Question 7 is A, so it will be 350. Yes, I'm right. Okay, so it will be 350 Newton. Okay, take note, common mistakes students tend to make is actually the perpendicular distance for F. They will actually use 50 cm or they will actually just reuse 70 cm again. But take note, perpendicular distance is always measured from the force to the pivot. Okay, that is the distance between them. Okay, so it will be 70 plus 50. So at this point in time, okay, if you're doing principle of moment at this level, at this point in time, okay, before your O level, you literally must actually know what do you define as perpendicular distance. So it's always measured from the pivot to the force itself. Okay, so be careful. Number 8, okay, pressure at the bottom. Okay, here I would say is an interesting question. Okay, whereby we look at pressure. Pressure, commonly known as pressure is force over area. Okay, and I think for this question, it's quite obvious that the area I'm looking at is actually at these surfaces. Okay, and the area I'm looking at, because it's at that surfaces, this area, I will do a simple math. It will be actually 6.0 meters square. So this will be the area I'm looking at. Okay, but what is interesting is where do I get the force? Okay, so this is the area. So now for force, okay, or what we call the weight, the force is actually this object here, which is actually the weight. The weight will be exerting onto this particular surface, the blue color surfaces, which is the force. Okay, so the weight, for this case, right, the force here will be the weight of the object or weight of the liquid, okay, which is divided by the area. For weight of the liquid is you have to like do a simple manipulation because you're not given the weight itself, you're not given mass actually, but you are given density. Okay, so let's do a simple formula. Okay, density is actually mass over volume. Okay, so if I want mass, it will be mass, then it will be density multiplied by volume of the object. Okay, so what do I do now is, what does mass got to do with weight? Remember the formula for mass and weight. Weight is actually defined as mass times gravitational field strength, which is mg, divided by area. And mass is where? This is the mass, which is density multiplied by volume. Okay, the rest remain the same. Okay, G will be here, area will be here. Okay, so now your formula, which is a simple F over A, okay, because you substitute density formula inside, you'll find that now your pressure formula is actually equal to this. Density multiplied by the volume times G divided by A. Okay, gravitational field strength is given. This is your G. This is my density. Volume, definitely easy to find. Volume is the 3 times 2 times 3. So that will be the volume. Okay, area is given here. I found the area just now. So in fact, I have everything ready. So once you have everything, you just substitute the variable into the equation here. Okay, and you'll get your answer to be exactly what you want. Okay, which is actually 24,000 Pascal. Okay. Now, things to take note is here what we do is I actually combine two topics. Actually, is under pressure, and I actually combine the formula for pressure, and I actually combine the formula for mass, weight, density, which is density. So if I combine these two formulas together, I will have actually a new formula here. Then I substitute the variable that is given to me. Okay, so take note of the handling of the math. Okay, the manipulation of the math formula. Okay. It's not an easy one. It's just tedious. I would say, yeah, it's not easy. It's just tedious. Okay. So just take note of the number. So don't make any careless mistakes. Like example, you calculate the wrong area. Instead of 6 meters square, you give me like maybe 9 meters square or something. Okay. So just take note of it. Number 9 and number 10. Okay. Number 10, I would say, number 10, you have to read the question carefully. Okay. The tank is made out of solid iron. Okay, so right side is iron, the other side is air. So air, straight away, if you talk about heat transfer, air is always a bad conductor. Okay, air is always a bad conductor. Iron is definitely a good conductor. Okay, now what happened is, straight away, if I'm looking at this question, right, if I'm looking at this question as what is given to me, whereby it's talk about air and iron, I'm actually looking at it as a medium. So I'm actually comparing the mode for this particular medium, iron versus air. So the common mode that they have is what we call conduction. Okay. So what is the main mode of transfer for white? Okay, X to white. Okay, X to white, the main mode, which is the fastest. Okay, it will be from iron, from X all the way down to Y. Because why is it the fastest? Because it is basically a good conductor. Iron is a good conductor because it's metal. Okay, so straight away answer I will know is B already. Okay, so take note of what clue the question is given. The question is given is you compare the medium, which is iron, and the other one is looking at air. Okay, which is a solid versus a gas. Okay, so the common thing that tie between them, if you look at heat transfer, is actually conduction only. Okay, radiations, you need to look at it as maybe size, color, and surfaces. Rough surface, iron has rough, or what are the surfaces given. Okay, so these are the clues to tell you that it's actually radiation or conduction or even convection. Okay, identifying the clue for heat transfer is very, very important. Now, for number 11, okay, number 11 here is a trick question. Okay, in the sense that there are certain clues that's hidden in the question here. Now, the question says the temperature remain constant. So when the temperature remain constant, right, one of the big clues that they are giving us is that the kinetic energy of the particle is actually constant. Okay, this is what we mean, because kinetic energy is proportional to the temperature. Okay, so if I have temperature increase, okay, I will know that the EK of the particle will actually be increasing. So if the temperature is constant, my EK will be constant. Okay, then the next thing is if I'm expanding slowly. Expanding slowly means the object is actually getting further and further away. So which means expanding slowly means the distance, the intermolecular distance, is actually getting further and further away. Okay, if not, how am I going to be expanding? Okay, so I expand, why? Because the intermolecular bonds is actually getting further and further away. So for question 11, what we are looking at is actually the green color one will be here. Okay, the green color, they are moving further and further away. Okay, this is what they mean, expand slowly. Then when I say the red color, temperature remain constant, okay, it actually means the speed, the average speed of the object actually, average speed of the molecules actually remain unchanged. Okay, so the clues actually to answer are given in the question already. So students need to take note or to be sensitive to what are the wording or what are the phrasing that the question is trying to hint them. And from there, they can actually deduce the possible answers, not like anyhow trial and error or any. Okay, so take note of the clues that's given to us. Okay, appreciate the clue, appreciate the question. Okay, so now number 12 is okay. Okay, number 13. Okay, number 13, a common mistake that I actually see when I mark the paper, okay, is that when I say 20 cm here, 20 cm is actually not the wavelength. Okay, here you must remember the picture here is each of the crests, each of the dot here, or each of the line represent a crest or many crests. Okay, so between the two dots, between the dots here is what I call the distance between crest to crest. Okay, so actually this dot is actually, between this line is actually one wavelength, one lambda. So there's actually one wavelength here, one wavelength here, one wavelength here, okay, and one wavelength here. So what I'm saying that, what the question is saying is actually, for the span of 20 cm, I'm actually looking at 5 wavelengths, okay, 5 lambda, which I can effectively saying that one wavelength is actually 4 cm. Okay, then after that, based on the questions, the frequency is given is 4 Hertz, okay, and I know the wavelength is 4 cm. So I want to find the speed of the wave, standard wave formula, V equal to F lambda. Okay, I will know the frequency is 4, the wavelength is 4, and I will get a nice answer called 16 cm per second, which is C. Okay, so take note of the question here. Okay, the important thing is to be sensitive to the clues that's given to us. Okay, very often students straight away see this 20 cm because it's distance. They will just assume it is the wavelength. Okay, in this case, it is not. Okay, it's actually 20 cm actually belongs to 5 wavelengths. And from there, you should be able to deduce what is actually the length of the, or what is the dimension for one wavelength. Okay, so you must know what numbers the markers are giving have given you, and actually what clues you need to do. Okay, so you need to be sensitive to the number that we have that is given to you. Okay, now 40 I would say is one of the questions that actually get a lot of people wrong. Now for 14 is, how do I know which object is which of the student can see how many students are? The easiest one is, let's say I have the mirror. Okay, so now let's say I extend the mirror a bit. Okay, so now let's say I extend the mirror. Okay, I'll extend the mirror. Okay. Now, so how do I know which part of who can see, which student can see which students are? The easiest one is we go back to the basic, go back to the property of the mirror. What the property of mirror, the easiest one that we can use is the property of mirror is the object, whatever distance the object is from the mirror, the image will be away for that same particular distance. So for example, if the student Z is, let's say, 2 meters away from the mirror, similarly, the image form of the image of student Z will also be 2 meters away from student Z, from the mirror. Okay. So this is what we mean by the property of the image itself, of the mirror. Okay. Image of the mirror means the distance in front of the mirror, whatever distance the object is in front of the mirror, the image will also be the same distance away from the mirror. These two distances are actually the same. And what you do is, based on light ray, okay, if my image of Z is here, I will call this Z prime, okay, Z prime, the image of Z. If I am able to see Z prime, okay, the image, the light ray from the image, okay, should actually enter the eye of each student with no problem. Okay, oops, just be careful. Okay, behind it should be dotted line. Okay, so just take notes. Okay, dotted line. Okay, because behind is virtual ray, so it's what I call fake ray. Okay, so student Y should be able to see student Z because that ray hits the mirror here. It's part of the mirror. Okay. Similarly, okay, if you look at image Z, X is able to see Z through this light ray. Okay. So X and Y actually can see Z. Okay, because the point of incident, okay, is actually on the mirror itself. So if you complete the light ray, okay, so let's say if I complete the light ray, okay, this will be what the light ray look like. Okay, object Z, you will go through. Okay, so same thing, the light ray will come from an object, it will hit the mirror this way. Then after that, it bounces back to the object itself. Okay, bounce back to the eye itself. Sorry, not object. It will bounce back to the eye itself. Okay, and X is able to see Y using this ray diagram. So you find that if you repeat the same thing for all the image, all X and Y and Z, you'll find that each of these students can actually see the remaining two students. So in fact, if you do this, if you repeat this for student Z, student Y, and student X, you'll find that actually all three students can actually see the image of each other. So that's why the answer for number 14 is actually B. Okay, all the three students are able to see each other, okay, from the mirror itself. Okay, there are shorter ways of doing it, like calculating the distance, all these things. But I'll find that drawing, if you look at the ray diagram, drawing is actually one of the fastest way to solve. Okay. Question 14. Question 14, to solve question 14, right? More often I have to remind students, you must remember the formula, the Snails Law Formula. For example, refracting index. There are two formulas that relates refracting index. It will be sine of the angle, okay, the angle in the less dense medium, divided by sine of angle in the dense medium. And the other formula that we look at is we look at the speed of the ray itself. Refracting index is actually the speed of light in vacuum, divided by the speed of light in the medium itself. Okay, in this case, of course, the common fact that we look at, the speed of light in the vacuum is 3 times 10 to the power 8 meters per second. Okay, but what is common about these two formulas is that they're actually looking for the same thing, which is the refracting index of the medium. Okay, which means if I'm looking at the same medium, A and medium P, okay, this formula, if I use the formula on the right, this formula, I should be able to get the refracting index of P. If I use the formula on the left, I should be able to get the refracting index of P. Okay, So in a nutshell, I'm saying that if I use these two formula, I should actually find, I'm actually looking for the same thing, reflecting index P. So I can actually safely say that sine L less dense over dense is actually equal to the speed of light, okay, divided by, okay, speed of light divided by the speed of in the medium. So if you put the equation together, it will look something like this. It will be sine less than sine dense equal speed in vacuum divided by speed in the medium. Okay, so this is the formula that you have when you combine these two formula together. Okay, so after that, what you do, you just substitute the value inside. One thing to take note is, other than this formula, one thing to take note is really, when you talk about light ray students, you must really remember where do we measure the angles. It's always measured from the normal to the light ray. Okay, it's always from the vertical axis, okay, from the normal to the light ray himself. So if you look at the math, you'll find that actually less dense is actually not 40, it's actually 50 degrees. Is this angle I'm interested? So it should be sine 50. Dense will be 24 degrees, so it'll be sine 24 degrees. Speed of light in vacuum is a fact, fact that you must remember is 3 times 10 to the power 8 meter per second divided by speed in the medium, which is what you need to find. Okay, so if you rearrange the math, you actually have the answer of speed of light in the medium to be speed of light in the medium, okay, to be 1.6 times 10 to the power 8. Okay, same thing, meter per second, which is B. Okay, so please take note of the math that's involved, okay, especially these two formula, okay, because if you forgot that there is these two formula, I don't think you can solve this question, okay, but if you remember them or if you know them, okay, you'll find that it's actually a like 30-second job, okay, so please take note of the formulas, know your facts, know your mathematics, okay. 16 and 17, okay, 16 and 17, 16 is quite like, I would say just remember like EM wave, all the spectrums, all the waves that appear, radio wave, gamma rays, X-rays, infrared, ultraviolet, all these things. You must know the position and the users. Okay, so this one, there's no two way about it. Number 17, okay, 17 you look at is when I say same pitch, first thing that comes to your mind, same pitch I'm looking at is actually same frequency. Okay, because pitch is actually frequency, a different presentation. But the original sound, okay, and it's quieter. Quieter means loudness is actually softer. Loudness, okay, has an impact on amplitude. So the amplitude is actually smaller. Okay, so what am I looking at is actually the wave, the reflected wave is actually a wave that has a smaller amplitude, but have the same frequency. Okay, and this will bring us to the answer. Okay. So you check which answer am I looking at. Okay, same frequency, lower amplitude. Okay, so you'll find that, if I look at lower amplitude, I don't have lower amplitude. Okay, oh, I have one lower amplitude, possible. Okay, then you find that actually for MCQ, you look, the more you see, you find a lower amplitude, right? You find that, there's no other choices really. There's only one D that is there. Okay, so straight away you choose the answer to be D. Okay, but if you want to work out, okay, no problem. Okay, now here take note, the underlying assumption that is hidden behind the question is these two sounds, okay, the reflected sound, okay, and the original sound, they are actually in the same medium. Okay, same medium. Okay, it will mean one thing, the speed actually remains the same. Okay, the speed of the two waves actually remain the same. Okay, and we all know that speed has one formula, V equal to F lambda. Okay, so if the speed remains constant, and I know based on the question, okay, okay, the frequency remains the same, what will happen to the wavelength? Okay, the wavelength, okay, based on the formula, based on math, you'll know that wavelength actually remains the same. Okay, which happens to coincide with the answer D. Okay, so of course, if you look at MCQ, okay, the moment you know you can narrow down the answer to be lower amplitude, which is only D, you straight away choose answer. Okay, so you don't, I would say, you don't need to work out the amplitude, the wavelength. Okay, you don't need to work out the wavelength. Okay, straight away you narrow down answer, you confirm, you are very, very sure that the amplitude is lower, and you only got one option with lower amplitude, is to confirm that will be the answer already. Okay, so 18, nothing much. 18, just memorize. I would say you just remember the charge, the electric field charges pattern. Okay. Then after that, fully charged battery, standard formula that we have. Okay, how much charges? Current. Okay, the only formula that links them together, current and charges, is the definition of current. Current is actually rate of flow of charges per unit, flow of charges per unit time, which is Q over T. Here, remember, the SI unit for current is always in seconds. So if you look at 5 hours, okay, remember to convert to second. 1 hour is 3,600 seconds. Okay, so 5 hours, you have to convert it to seconds. Okay, so when you do look at a map, charge is actually I over T. Current is 3 amp. But the hour here I'm looking at is 5 hours, but I need to convert it to seconds. I have to convert to seconds. So please take note of the booby trap here. Okay, convert to seconds. If you convert everything to seconds, you punch your calculator, you ask your calculator to get the answer, you'll know that, okay, the answer will end up to be D. Okay, 54,000 charge coulombs. Okay, that will be simple as this. Now, last question here, same thing. Last question, the formula that we are looking at is R resistance formula, which R equal to rho L over A. Rho here refer to the resistivity. Okay, so now you'll find that the same wire, okay, the same wire now, the same material. So between the two material will have the same density, between the resistivity will be the same. So this will remain the same. The length-wise will be 2 times. Okay, length-wise, this length actually will be 2 times. Okay, area of the object, it will be half times. Okay, area of this guy will be half times. Okay, so which means what I'm looking at, if the area, if the length increased by 2 times, the resistance will actually increase by 2 times because they are proportion. Okay, then secondly is if the area increased by 2 times. Okay, oh sorry, the area increased, the area reduced by half. The area reduced by half. Okay, remember area is inverse. Smaller the area, the bigger the resistance. It means the resistance will actually increase by 2 times. Okay, so the first time when you look at length, the length increased by 2 times. Okay, then after that, because of area, the area increased by another 2 times, and the resistance increased by another 2 times. So you actually get 2 times increment. Okay, over a span of the what is stated in the question. So 2 times 2, you'll find that the resistance of the wire actually increases by 4 times. Okay. The other way of looking at this question is you look at it in terms of mathematical manipulations. Okay, this one I will not dwell too much into that because I have done it in class already. Okay, so if you're interested, you can actually look at my video on chapter 15, I think, on electricity. Okay, there's one example that is quite similar to this, which I dealt with it using the mathematical formula. Okay, you can go and take a look at it. Okay, that is actually quite important because sometimes it's quite hard to reason it out using without numbers or without any formulas. Okay, so you can take a look at that video in the topic of electricity. I think is this is electricity chapter 15. Okay. Now for paper 2, okay, now we come to paper 2. Okay, paper 2 wise, okay, same thing as before. If you need any particular segment, okay, just go and just scroll down to the particular area. Okay, don't need to run through the whole thing. Question 1, I will not go too much except 1B. Okay, 1B is a very common thing. Okay, 1B. Okay, how we improve the accuracy of the readings? Okay, you can do it by taking different positions. Okay, so if you look at the the object, yeah, I can use the vernier caliper, I can clip it to the front of the object, or the front side. That's one position. After, I can clip it to the middle position, and the last one, I can actually clip it to the tail end. So I clip the vernier caliper at 3 different positions. Okay, and importantly is after taking the positions, I need to take average for the readings. If not, I will end up with 3 readings. So it doesn't improve anything. So what I have now is, if I take the average, I will be able to get a better readings, okay, for the thickness of the, I think it's thickness of the book. Okay, so remember the keywords that we're looking at is different positions and take average. Okay, now max and minimum. Okay, max and minimum, the technique that we look at is max and minimum. Why do you want the max and minimum? Why do you want to do the max and minimum? It's because, right, once I get the max and minimum, I will be able to know that, okay, any number between max and minimum, the forces it will be able to achieve. Okay, so 10 and 14 Newton, if I have the minimum, meaning what is the minimum means one side is 14 Newton, the other side is 10 Newton. So they are opposite directions. So 10 and 14, the difference, the F nets will be 4 Newton. So the minimum forces I'm looking at is 4 Newton. The maximum forces I'm looking at, the maximum force I'm looking at now is, if I'm looking at the maximum force, okay, maximum force, it means both of them has to be in the same direction. So one is 14 Newton to the right, the other one is 10 Newton to the right. They are in the same direction. So the net force here I'm looking at is 24 Newton. So my max is 24, my minimum is 4 Newton. So what we are saying that once I find the 14 and 24 and 4 Newton, why am I saying that at between 4 to 24, okay, if I have these 2 forces acting on the body, any number between 4 and 24, I am able to achieve that number. Okay, it's just that I need to change maybe the angles between 10 Newton and 14 Newton. Okay, so at different angles between 10 Newton and 14 Newton, I will be able to achieve the numbers between 4 to 24 Newtons. Okay, so that's the idea of me getting the max and minimum. Max and minimum forces, it tell me what are the possible forces that can appear on the body, okay, by acting on 10 Newton and 14 Newton. Okay. Then after that, tip to tail or parallelogram. Okay. 2 forces acting on at 120 degrees apart. Okay. The vector diagram here, I will not dwell too much. If not, it will be a lengthy video. Okay. So for vector diagram, if you are still not sure, okay, you can look at I think chapter 3. I have a video. I have 4 videos or 3 videos on vector diagrams using parallelogram method and tip to tail method. Okay, whichever method that you are comfortable with, okay, you can use them to solve for this question. Okay, the idea is all the same, the common traps and the common presentation. Okay, so please go and take a look at the video at chapter 3, vector diagrams, where to get yourself familiar with this style of question. Question three, I would say is a tricky one. Okay, question 3, okay, please take note. Okay, the question asks for the CG of the cube. CG of the cube means what? CG of the cube means it's at the center of the cube. Because this cube is a uniform cube, it will be the center here. So at the center here, I'm saying that it's actually 0.06 to the right, and it's 0.06 to the left. Okay, so effectively, if the length is 0.28, okay, the distance between the edge of the table to the CG of the table, it will be here. Okay, this will be the length between them. So it will be a standard example. If you look at the picture, it will be 0.28 minus 0.06, you get answer 0.22. Okay, now this horizontal distance, the importance of this horizontal distance is actually this. Okay, this actually tells us, this is actually the perpendicular distance between the weights and the pivots. Okay, this distance is actually what we call dW. Okay, they are another name for the distance for part A is called the perpendicular distance, okay, for weight. And your weight is here. Okay, let's use a different color. Okay, so this is your weight. Okay, and weight is pushing down. The pivot is here. You'll find that the moment by weight, it will be a clockwise moment. Perpendicular distance I mentioned is called dW. Okay, so this will be the weight of the cube. The weight of the cube given is how much? 3.5 Newton. Okay, so it will be 3.5 multiplied by d perpendicular. Answer will be 0.77 Newton meter. I will not say this is difficult. Okay, just be careful of the math, especially part A. Now, same thing. What is the minimum weight of the platform required to set up to balance the object or to balance the setup? Okay, same thing, the weight of the pivot. Now, based on the questions, right, the weight of the pivot, okay, the weight of the ruler, okay, the weight, the ruler, the platform, there's a weight, okay, at the edge of a 0.75 uniform platform, it will mean that the CG is in the center. Okay, so which means if it's 0.75, half of 0.75 will be how much? 0.75, half of it will be 0.375. So I can safely say that the weight is actually here. Okay, so this is 0.375. Okay, let me draw it slightly more accurate. Okay, so you'll be okay, 0.375 meter, 0.375 meter. This is where will be the CG of the platform itself. Okay, and the ruler, the weight of the cube, 3.5 Newton is the weight of the cube. Okay, so if you look at this particular drawing, right, you will know that, okay, the perpendicular distance, the weight is here. Okay, the perpendicular distance between, if I look at a moment, okay, you will know that the weight of the platform is actually an anti-clockwise moment. And you will know that between the pivot and the weight itself, it will be the perpendicular distance of the platform. Okay, remember the perpendicular distance based on this picture is not 0.75, it's actually dp. Okay, so you must know where to find dp. Okay, so first thing is find dp, and I think it will be quite straightforward. Okay, why? Okay, because 0.75, this is 0.28. Okay, so effectively based on the question, this part is 0.28. Okay, and I know this part is 0.375. Okay. Okay, so if I am to take the difference between them, okay, the difference between them, it will be what we call this distance. This will be called dp. Okay, so dp is actually 0.375 minus 0.28. Okay, so this is where I have the perpendicular distance, 0.375 minus 0.28. Okay, so maybe what I do is, let's see whether I can shift the drawing here. Okay, let's see if I shift the drawing here. Okay. Maybe it's easier for you all to see. Ayo. Okay, I'll shift it here. Okay, this is how I find the perpendicular distance. Okay, so take note of where I find the perpendicular distance. Then after that, what I do is anti-clockwise equal to clockwise moment. After that, I use principal moment, I just solve it. Okay, now for question 4. Question 4, okay, tumbling 8, it will be on stability. Okay, stability wise, take note of a few things when we talk about CGs, all these things. Okay, what's the purpose? The CG, when question 4.1 saying that the CG is here, the idea of me giving you a CG, it actually tell you where is the weight, okay, of the object. Okay, it's always from the CG all the way vertically down. So this will be the weight of the egg itself. Okay, so now the purpose of lining the leads, okay, is actually to lower the CG. I would say this question is quite straightforward, nothing fanciful. Now, the problem is in the second question, okay, part 2. If I knock over the tumbling 8 at figure 4.2, I knock over already. Okay, draw an arrow to show how the weights of the object acts when it get knocked over. So at this position here, remember the idea of the CG is it tell you where is the weight. So the weight will still be at the CG, whether the egg is upright or tumbled down horizontally. And one thing about weight is you must know it always acts vertically downwards because gravity pull down. So what we do is it will actually be still vertically downward. It will still be here. Very common mistakes that students make is like because I know part 4.1 the weight is pointing down towards the what I call the tip of the egg, so they will tend to draw the weight this way. Okay, to follow this question, to follow this answer. Okay, and this is one of the big mistakes that we are looking at. Okay, whereby the student just copy the picture without understanding. Okay, remember weight. When we look at weight, is by the gravity, it has certain property. Okay, weight of the object always happen at the CG, and it always point vertically down. Okay, because gravity always pull downwards. Okay, so take note of the answers. Take note of how I get it. Okay, so don't fall for this trick again if it ever come out in exam again. Now, how does the eggs get upright? Okay, this is what we mean by stable equilibrium. Okay, so some of the keywords that we have for stable equilibrium, you must remember. Okay, now the pivot is here. Okay, and because the weight and the pivot, there's a distance between them, the weight will actually has a clockwise moment about the pivot here. And it's because of this pivot, this moment, okay, you'll find that the egg will actually be swing upwards. Okay, so you will actually rotate clockwise, the egg will actually swing upwards straight away. Okay, and this is why we call this tumbling egg is actually quite difficult to actually fall down. Okay, because of the position of the CG, which is lower than usual. Okay, whenever you push it horizontally, because of the clockwise moment, okay, there will be always a perpendicular distance between them. And because of the perpendicular distance between the pivot and the weight, there will be a moment, the clockwise moment, to actually return the egg back to the upright positions. Okay, so you look at explanations, the highlighted in yellow are what we call the keywords that you need, okay, to present your answer to the marker. Okay, so please take note of them. Okay, don't write anyhow and anywhere you want, okay? Because if you look at, in terms of exam, you look at marking, okay, the examiner actually is looking out for students to display their understanding of this particular physics concept. Okay, not their English composition skills. Question 5 is straightforward, so I will not dwell too much. Okay, question 6. Question 6 here we are looking at is a thermal property, melting, heating question here. Okay, first thing first is the question look at it as a liquid. Okay, so the moment you say liquid means this is actually what we call a heating phase. Okay, and because it's already a liquid, this particular phase here is actually not melting because it's already a liquid already. So this one is what we call boiling. Okay, so this stage is already a boiling. So how do I know this one not melting? Because the question says it's a liquid at the beginning. Okay, then after that, the same keywords we will talk about it. If I'm looking at kinetic energy, if I look at in terms of internal energy, I will always look at it in terms of two types of energy: the internal kinetic energy and the internal potential energy. Okay, different stages, the energy will behave differently. Okay, but because of that, the answers to this question is actually quite predictable. Okay, so now, same thing. If I look at internal energy, what is internal energy? Internal energy, students sometimes tend to forget. Internal energy is actually encompassing these two. It's an overarching word to group all this energy together. Is what we call internal energy of the molecule itself. Okay, so at this motion here, at heating, okay, student must know at heating, your temperature is increasing. So actually your EK is actually increasing, and your potential energy, because there's no change in phase, okay, actually your potential energy should be constant. And similarly, okay, if you look at boiling, okay, boiling, there is no change in temperature. Okay, why? Because all the energy has been used, is been pumped to changing the state of the substances, which is the potential energy, which is I'm changing the intermolecular distance, which is why at boiling, the potential energy is always increasing. But because of that, my kinetic energy is actually remains constant because all the energy is being diverted to potential energy. Okay, so these are how the energy of each of the stages will change. And similarly, because internal energy consists of both of them, so EK increase, EP constant, but my internal energy will still be increasing. Same thing for boiling, EK constant, EP increasing, the internal energy will also be increasing. Okay, so with this, you actually have the answer for part A already. Okay, which is region X, increase, constant. Okay, likewise, Y will be increase, constant, and increase. Okay, so you check which section you're looking at. Okay. Now for part B, the standard when you talk about region Y, why no change in temperature in region Y? This, I would say the question is quite standard because for thermal property, the question they always ask is why there's change in temperature during heating phase, which is this particular region. Why the temperature actually remain constant at this particular range. It is always quite standard one. So these answers are actually quite, I would say it's a hot favorite. So students, you have to be sure that you cover all bases before you go for your exam. And we talk about no change in temperature means the energy, like I mentioned before, is being used to diverted to PE, the potential energy, to do what? Okay, to overcome the intermolecular bonds. Okay, and now because you are gas changing to from liquid changing to gas, so the energy other than break bonds, you have one additional component is actually to push back atmospheric pressure. Okay, so these two are the two main users for potential energy, where the thermal energy, the heat is gone, the heat is diverted to increase the potential energy to break bonds, okay, and to actually push back atmospheric pressure. And likewise, the last one is tell the marker to say that all the energy is diverted to EP, none is going to EK. So that's why no change in temperature. Okay. So please know what you're writing, know what you're doing. Remember to cover all bases before the exam. For transverse wave, question 7. Okay, question 7, I will not after marking, you will find that the common mistake that the students have is actually careless mistakes. Okay, for part A and B, part A, remember, the question say 1 square is 2 cm. Okay, so literally, if you look at wavelength, okay, one wavelength is actually from R all the way here. Okay, one wavelength is actually from R all the way down here. This is one wavelength. Okay, so one wavelength is actually 1 square, 2 square, 3 square, 4 square. So one wavelength is actually 4 square. 1 square is 2 cm. So 4 square is actually 4 times 2 cm, which is actually 8 cm. Okay, so your wavelength is actually 8 cm. And the other mistake that we students tend to make is this interpretation, 10 oscillation in 2 seconds. 10 oscillation means 10 cycle or 10 wave or 10 cycle in 2 seconds. Means I have 10 cycles in 2 seconds. Okay, one cycle. Okay, or one cycle, I will have one cycle. I will literally have 2 divided by 5, 2 divided by 10, 0.2 seconds. Okay, this time for one cycle is actually what we call period. Okay, the period. Okay, and if my period is 0.2 seconds, frequency, which is 1/T, okay, it will bring us back to 5 Hertz. Okay, so the wave for this, the frequency for this wave will be 5 Hertz. So before you do anything, right, you actually need to get ready all the all the variables here, which should actually take you less than, I would say, 30 seconds or 20 seconds maybe. Okay, but just take note of the possible booby traps, the 2 cm, and actually the 10 cycle and 2 seconds. Okay, some of students actually mistaken that when we say each particle is 2 seconds, they thought that one cycle is actually 2 seconds. Okay, which is one of the common mistakes. One of quite common mistakes. Okay, so once you have all this, you can actually proceed on to find the speed of the formula. Okay, the speed of the wave itself, which is v equal f lambda. Okay. Now, the final one that we have is the waveform at 0.5 second later. Now, 0.5 second later, what is 0.5 second later? Okay, given just now in the beginning, you'll find that the period is 0.2 seconds. Okay, 0.05 is actually, when you talk about when you talk about t is 0.2 seconds, is literally I'm saying one cycle is 0.2 seconds. So when we talk about 0.05, compare with 0.2 seconds, you'll find that 0.05 seconds is actually a quarter of a cycle. Okay, one cycle is 0.2 seconds, so 0.05 seconds is actually a quarter of a cycle. So literally, I'm talking about is the question here, the waveform at a time 0.05 seconds is actually telling you to draw the waveform after moving for 1/4 cycle. Okay, so if it's moving to the right, okay, 1/4 cycle, one cycle here is this. This is one cycle. Or to be exact, one cycle is literally 4 square. Okay, 4 square is one cycle. Okay, 4 square is one cycle. So if I'm looking at 1/4 cycle, I'm literally asking you, okay, to actually shift each of the dot by 1 square. Okay, because remember, one cycle is 4 square. So 1/4 cycle will be 1 square. So which means each of the dot here will actually shift right by 1 square. So all the dots here, you will shift right by 1 square. Okay, so what we are saying is that this dot used to be here, you will shift 1 square to this blue color. This dot used to be here, you will shift 1 square to the right. Just 1 square. Every dot you shift is shift 1 square. So if it's this particular dot, you shift right 1 square. Okay. So if you do this for all the graph, all the points, you'll find that the new particle will be the blue color one. Okay, join all the blue color dots together, you literally have the wave for 1 cycle, 1/4 cycle later. Okay, so this one, the dot, you shift right for 1 square, you'll be here. Okay, so the blue one will be the wave for 1/4 cycle. How do I know it's 1/4 cycle? Because 0.5 and 0.2, 0.05 and 0.2 second, the difference is a quarter. So literally 0.05 second later, it literally means 1/4 cycle later. But I would say among all the section A questions, this particular question, I would say, is one of the toughest, really. It's one of the toughest. Okay. Describe the wave motion. Okay. I would say is they are both are related. Okay. For example, initially R is here. Now the same dot R will actually be here. Okay. So which means the dot which R will actually be moving upwards. So the motion of R for this case is as the wave moves to the right, the R move upwards. Okay, because it's transverse wave. So it has to be up and down perpendicular to the motion. How do I know it's upwards? Like I mentioned before, it packs with the before and after. Before R was here, after moving 1/4 cycle, R is on top. So R is actually moving upwards, or had moved upward already. Okay. I would say question 8 is a standard refractive, is a standard, it's a standard internal refraction or a refraction question. Common mistakes, please take note, do not make is this angle 35. This angle 35, okay, remember, it's not my incident angle. Sorry. This angle 35 is not my incident angle. Incident angle is always measured from the normal, okay, to the wave itself. Okay, so it's actually should be 45 degree. Is it 45? No, it's 55 degree. Sorry, my math. Okay, so it's actually 55 degree. Okay, Then after that, reflecting index given is 1.5. Same thing, you plug in the formula, you should get the answer to be 33 degree. So the wave will be 33 degree here. Okay. Like same thing for part AB, surface AB, which is here. This is surface AB. Okay, this particular surfaces here. Okay. Calculate angle incident of the ray at surface AB. Yeah. Incident of the ray, it means I want the normal is here. Let's say normal is here. I want the angle to be here. This is the incident angle. Okay, with the arrow. Okay, this is the angle incident that I want. This angle, this is what I want. Okay, the black color one. Okay, squeeze it in here. Okay, how do I get the angle here? This question is a geometry question. Okay, based on the question, okay, you will know that the angle here is 45 degree. Angle in a triangle is 90 degree. Okay, this is 45, this is 90. This will be 45 degree. Okay, and if this is 33 degree, this angle here will be, let me do my math. 90 minus 33, it will be 57 degree. Okay, 57 degree, same thing, this angle here. Okay, angle in a triangle is 180 degree. So 180 minus 45 minus 57, you end up with 78 degree. Okay, so we know that normal is 90 degree. So this section here is 90 degree. So I will say that angle I plus 78 degree, it will be 90 degree. So I will be able to find angle I is how much already. Okay, which is what is shown in this drawing here. In this answer. Okay, this is how I get the working here. Okay. So take note of the working, take note of the answer. Okay. If you are not sure, okay, you can refer to this diagram. It's a bit messy here. Okay, but primarily what I'm doing is I'm looking at a bit of geometry, angle in the angle, total all the angles in the triangles. I'm looking at 90 degree complementary angle, all this. Okay, to solve this I would say math question, but it's part of the refraction context. Same thing, when I exit the surface, will I exit surface B or will I do a total internal reflection? Okay, the answer is actually yes. Okay, how do I know it's yes? It's because the reflecting index is 1.5, if I'm not wrong. Okay, so you have to work out yourself. At the back end, you can work out the reflecting index is 1.5, which means I can actually find the critical angle. Okay, so which means I can find the critical angle is reflecting index is 1 over sine C. Okay, this is 1.5, 1 over sine C. So if you look at the map, I can actually find angle C, okay, to be 1 divided by 1.5. After that, I inverse sine. Okay, it will be 41.8 degree. So critical angle will be 41.8 degree. Okay, now if critical angle is 41.8 degree and my angle is only 12 degree, so definitely my angle I is actually smaller than angle C. Okay, and if my angle I is smaller than angle C, I will not do a total internal reflection. Okay, so take note of how I solve the question. I literally need to find the critical angle first. Right, on my own, I need to find a critical angle before I make a judgment call to say, hey, does it internal reflect or does it not internal reflect? Okay, so please know a question carefully. Then after that, you have is question 9. Question 9, ray diagram. Okay, ray diagram, I won't dwell too much. Okay, most of you should know how to do it. So I will skip question 9 straight away. If you got problem, just drop me an email or just drop me a comments at the video bar below, okay, so that I can actually run through the question. Okay, if you need question 9 and 10, I will skip it. Okay, because it's I would say it's a memorized question. Okay, it's a straightforward question. As in, for these two questions, not a big problem for my students also. Okay. Question 11. Question 11. The only problem I have is that how we define 150 kilohertz. Okay, 150 kilohertz. Okay, now when we ask for nowadays, when we ask for like explain something in details, we are not just looking at the definition. For example, most of my students know that 150 hertz it refers to frequency. So for the answer, for them, they will write part A, right? Their answer will give me a very standard definition for frequency. Is the in 1 second, how many complete is the number of complete cycles. The number of complete cycles is the number of complete cycles in 1 second. Okay, this is a good definition for frequency, but it doesn't answer the question because the question doesn't just ask for frequency. He specifically asked for 150 kilohertz. Okay, in explanation. So the thing that students need to like actually go beyond is actually to pack these standard definitions and answer it with respect to the question. And all the students need to know is just phrase the answers accordingly and answer the question, whereby they just need to include the word 150,000 complete waves per second. Okay, remember, you are not just I'm not just asking you to define frequency. I'm asking you to define a particular frequency, which is 150 kilohertz. So you need to explain it according in context. Okay, after that, 11, not much of a problem. Then question 12. Okay, question 12 is light charge and unlight charge. Okay. For this context here, filter, there are two filters based on the questions. Okay. The question here we are looking at is after the dust particle went through the first filter, okay, which is the first filter. After that, he went through a second filter, and what happened after that? Okay, remember there are two filters that's in context here. So what in your answer you have to tell me is that when the dust particle passes through the first layer, okay, it will be a charge. When I pass it through the first layer of filter, the dust particle actually get charged. It becomes positively charged. Okay. Now, here, when the positive charge particle here, I'm only referring to the dust particle only. Because the dust particle, which is slightly bigger size, they will get charged out as compared to the air particle. The air particle being smaller, they will not be charged. So after passing through the first layer, you'll find that the dust particles are being charged, but not the air. So after that, what we do is, I have the second layer, which is negative charge. Okay, now I have a negative charge layer. Okay, now I have a negative charge layer. Negative charge, positive charge. Okay, I will have what I call unlight charges attract in the second layer. Okay, so after passing through the first layer, the second layer, what it does is it actually make use of the electrostatic attractions, whereby you look at the light charge and unlight charge. Okay, they will actually attract each other. Okay, and the charge particle the charge dust particle here, the positive charge dust particle actually will be attracted to the dust filter with the second layer of dust filter. After that, okay, the dust particle will stay at the second filter. And after that, my air particle will actually pass through the second air filter. It will come out as clean air. Okay, so this is what we are looking for in your answer. Okay, in the answer, the student has to tell me what happened to the second layer. After that, after the dust particle has been attracted, what happened to the remaining air particle? So you will be able to pass through the air filter easily. Okay. Part B, positive charge is a standard question. I will not dwell too much here. Okay, so please know the charge pattern in your textbook. Okay, know why.
Okay, now we will be looking at section B. Okay, section B here, take note for all students. Remember, I will need you to select 2 questions. Okay, so during the assessment, right, remember to read through all the 3 questions first. Okay, don't just see the first question, then you start doing it. Okay, read through all the questions first. Okay, all the 3 questions. Then after that, identify which of the questions you are like most comfortable with, which question can you score, which question are you having like you find it the easiest. Okay, don't just do question one because it's just the first question. Because sometimes the first question may not be the most straightforward one. And similarly, the last question may not be the toughest. Okay, it might be like the last question could be the one of the most simplest one, the most simpler. Okay, so remember, read the question first, then choose the correct two question, or to be exact, choose the two best question. Now for question 13, you have a 10 kg mass, what you have on the question here. The difficult part about this question is that this question has a graph which is broken into two sections. One is the first 20 seconds, which is here. Okay, the first 20 seconds. Then followed by the second segment of the graph, which is the 5-second segment. Okay, now on this section here, right, take note, okay, of the information given to you. The information is that there is an acceleration for the first 20 seconds, okay, which is 2 meters per second square. Okay, now for the first section of the picture, okay, where the acceleration is 2 meters per second for the entire 20 seconds at a force of 40 Newton. Okay, so this 40 Newton is the applied force. Okay, then after that, once you're okay with the questions, then you start to look at 4A and you start to solve whatever questions that come your way. For example, the first one that we're looking at, first one is the question asked for the brief explanation of what does it mean by acceleration of 2 meters per second square. Similar to section A, whereby we ask you to define a particular frequency. In a usual context, the question will ask like define or explain what is acceleration. So the students will give a very standard question to say acceleration will be the change in velocity per unit time. Now, but for this particular question, right, you cannot just define acceleration because the question asks for a specific number, 2 meters per second square. So if you look at it as a type of definition, you have to make sure that you craft your definition to answer this question, whereby you need to answer the question to say what does it mean by 2 meters per second square. So the standard answer will be, if you look at acceleration, it will be the change in velocity, okay, per unit time or per second. Okay, this is the standard answer. But this question, you'll find that this answer doesn't answer the question because you have not explained what it means by 2 meters per second square. So what you need to do is just tweak your answer a bit, okay, such that or craft your answer to suit the question that's given. So what you need to do is you need to factor in the 2 meters per second square. So for acceleration of 2 meters per second square, it actually means that the change in velocity is actually a 2 meters per second change in 1 second. That's what the question wants you to do. The question wants you to actually craft your answer with context or with respect to the question. You need to answer the marker question, not just your own question. Okay, so if we ask you for the definition, a standard definition for the acceleration, okay, you just go ahead and write change in velocity per second. But if they ask you for acceleration of 2 meters per second square, you have to make sure that your answer actually factor in that small additional thing, which is 2 meters per second square. So for those who are like looking at different, like memorizing your definitions, please take note that nowadays markers usually hardly ask like students to actually just write out the definitions, which everybody knows actually is in the textbook. So what the marker generally do is they will ask for the definition, but they have a context to that definition. So you must remember to actually craft your answer to suit that context that is given. Then you will get the marks. Then you will what we call answer the questions. Okay, so please take note of that. Don't just write down the definition blindly. Okay, second part, what is the speed of the mass at 10 seconds? Now at 10 seconds here, okay, given the 10 seconds, given the question, the graph may refer to the picture. The graph, the pictures is more important, okay, than just the question itself. Sometimes the clues to solving the questions lies in the graph. At 10 seconds, based on the graph, the acceleration is actually 2 meters per second square. Okay, then after that, one of the important clues given in the question is that the object actually start from rest. Okay, start from rest. And this statement, when you say start from rest, I always emphasize or tell the students, start from rest has an important keyword, means the initial speed is actually 0 meters per second. Okay, and this actually serves us in serve us to find the acceleration. Okay, in the formula, Okay, so when you look at this question, find the speed of the object at t equal to 10 seconds, you know that the acceleration is 2 meters per second square. And you also know that the initial speed is actually 0 meter per second. So with this combined, with these two values combined with the acceleration formula, okay, you actually can work out the final speed just by substituting the correct values into the formula. Okay, so take note, all the values that you see here are actually given in the question. So students, you need to actually be alert to see what are the clues that the question give you. Okay, when the question says at rest, it just means that the object is not moving, but what is the underlying meaning? What are the underlying information the marker is trying to tell you? Okay, you have to make sense out of that story. So after substituting number into the formula, you get 20 meters per second. Okay, that's the final speed. Then after that, the next part, we move on to a very standard question whereby they ask you what is the distance traveled. Now, here take note, right? For most students, the first instinct you do when the question asks for distance is you like to use the standard formula, which is speed equal to distance divided by time. You like to use this formula. Now, this one, I believe most of the tutors or teachers will actually tell you when you deal with speed equal to distance divided by time, this particular formula is useful if the motion is going on with a constant speed. If it's not a constant speed, increasing speed, changing speed, all these things, this formula is practically useless. And so that's why don't jump straight into using this formula. This formula actually does more harm than you think. Okay, so when we look at distance, the first thing that should come to your mind when you see the word distance, the first thing that comes to your mind should be your kinematics, and to be exact, should be area under your VT graph. Okay, area under VT graph, this particular concept or this particular approach actually solve any distance, okay, for any motion. So be it whether it's going at a constant speed, whether it's increasing speed, decreasing speed, you can actually use area under the graph to calculate distance. Okay, speed is equal to distance divided by time. Remember, this formula can only be used to calculate distance when the object is traveling at constant velocity only. So there's limitation to it. So for this particular question, if you want to find the speed at 10 seconds, okay, you need to have the first thing, the speed time graph. Okay, so you need to get your own speed time graph. Based on the information, okay, initially the object is at rest. So the first point you know is time 0 is here. V time 0, the velocity is 0. And you know that at time 10 seconds, based on the question, the speed is 20 meters per second, which is here. Okay, which is this particular point. So between 0 to 10 seconds, okay, what line should be the velocity time graph? It's actually a straightforward answer, okay, if you know where to find the clue. The question mentioned that the acceleration is constant acceleration, which is a fixed number. Constant acceleration in kinematics, it means it is actually an upward sloping line in terms of VT graph. It means that the velocity time graph is a straight line with a gradient 2 meters per second square. That's what the question is trying to tell you. The gradient of this line is actually a constant, which is 2 meters per second square. Okay. So with that information, you know that the speed time graph is a straight line, and you know that at time 10 seconds, velocity is 20 meters per second, meter per second. And if I want to find the area under the total distance, I will be looking at the area under the graph, which is this triangle here, with a base 10 and a height 20. So if I want to find distance, all I need to do is I just find the area under the graph, which is a triangle, by using the standard triangle formula, half base times height. The base is 10, the height is 20, and you will have the distance traveled by the object, which is the area of the triangle, which is 100 meters, okay, for that first 10 seconds. Remember, the common mistake that I see so far is that students always like to jump straight to using distance divided by time, and after that you get everything messed up. Okay, so for kinematics, okay, remember, kinematics, there are certain rules and there are certain conditions towards each formula. So you must know actually what each formulas or each concept entails. Okay, now the part D, we'll look at the frictional force between the mass and the rough surface. When you talk about frictional force, the first thing that comes to your mind should be actually straight away Newton's law, because this is one of the common approach that we see for to find frictional force. Okay, so if you have an object, okay, which is being pushed, Okay, applied force, and there's a friction here at between the surface. Look at how I draw. Friction, if I ask you to draw, remember, always draw between the surface, not any other place. The location does matters. Okay. Now, the forward force, okay, the applied force, remember, go back to the question. The question already say at 0 to 20 seconds, the applied force is actually 40 Newton. Okay, so, and on these blocks, okay, 40 Newton, the force is 40 Newton. The acceleration given by the object by the question is A equal to 2 meters per second square. Okay, these are the information that's given to you. Okay, so now same thing, Newton's law, we look at resultant force, which is the sum of forces. Okay, so if you look at the resultant force, the forces we are looking at is actually your applied force and the friction, just two of them only. And the motion is going to the right. So I'll take right as positive. So you end up with the equation 40 big F applied force minus friction equal to MA. A classic example. Okay, if you can't see, let me zoom in for you. Okay, so if you submit all the value, you will find that you'll be able, friction is unknown. So you use a basic algebra, you will be able to derive an answer to have friction is 20 Newton. Okay, so I would say that the approach that I use for this question, I will not say it's complicated. It's just that it is a standard approach for most of the Newton's question that you see in the textbook or even at other papers. The only difficulty that I think students might encounter is actually deciphering the information from the question. Okay, so the only thing from experience, I would say that try to dissect the question part by part. Okay, look at it as individual sentence by sentence to see what are the clues that's given to you. Then from there, you actually list out all the factors that are given to you, and maybe by listing them out, okay, the question may not be so daunting, and it might be easier for students to approach that particular question. Okay, now, part E here, this section say at 20 seconds, okay, the force decreased to 20 Newton based on the graph. Okay, and remain constant for the next 5 seconds. And after that, they ask you to explain certain things. Now, for 20 to 25 seconds, 20 to 25 seconds, the force actually dropped down to 20. Now, what the underlying meaning, okay, the meaning behind this particular phrase that students need to take note is that other than telling you that the applied force is 20 Newton, okay, other than telling you that the time is 20 seconds to 25 seconds, okay, this 5-second interval, there's one hidden information that's in these two sentences, which students need to sieve out because it's a very, very, very common booby trap. Okay, the information that is hidden behind is that the surface of the floor is actually remaining the same, which means that what am I writing? The surface, okay, remains the same. In other words, the question is trying to tell you that the friction experienced by the object actually remains the same at 20 Newton. Okay, this is the underlying meaning or underlying clue or reminder that the question is trying to tell you, to remind the students that the friction is still 20 Newton. So the force that experienced by the object now at this instance is actually a forward force of 20 Newton. A forward force of 20 Newton. Then after that, you have a opposing force of friction of 20 Newton or so. This 20 Newton is by friction. Okay, if you take the simple resultant force, you'll find that the forward force and the resultant force is actually the same magnitude. And in fact, if you do the simple Newton's law, okay, F net equal to MA, you'll find that the F net is actually 0 Newton. Okay, and 0 Newton is what we know as your Newton's first law. Okay, the resultant force is 0, aka the object, okay, will experience 0 acceleration, which is 0 meters per second square. And 0 meters per second square doesn't mean it stopped moving. There's two conditions for Newton's law. Okay, you must look at the initial motion. Okay, Newton's first law states that if the initial motion is stationary, the object will continue to be stationary. But however, if the object is already moving at constant speed, if resultant force is 0, the object will actually continue its motion, or it will continue his constant motion, or he will continue traveling at the same speed. Okay, that's what Newton's first law described. Okay, so for this question, students have to be careful is that when using the clues, you will be able to derive that the resultant force is 0. And when it's 0, it means that the object which is original moving based on the previous question, part D and part C, okay, the object will still continue to move at the same speed. Okay, and that's what Newton's law describe. Okay, so you have to be careful what you are what questions or what clues you are actually you are handling. For part C now, and for part 2, okay, at 25 seconds now. At 25 seconds, remember, the question says that at 25 seconds, the force actually disappears. It actually decreases to 0 at 25 seconds. So which means that at 25 seconds, right, the box that you're looking at, there's no forward force anymore, but there is still, the meaning behind the statement is there is still friction. The object which is moving just now, okay, at a certain velocity. Just now he was moving. At 25 seconds, when I remove the forward force, the object is still moving. He still has a speed. Okay. But at this point, the only force that he experienced is only the friction. So now the friction will be acting like a retardation force to slow down the particular object. So which means that the resultant force that you see here, at this particular instance, the net force experienced by the object is not 0. There's 0 applied force, yes, but the net force experienced by the object is actually still one force acting on the object, which is the friction, which is your negative 20. Your friction, which is opposing the motion, which is what the negative sign refer to. Okay, so there is still a force acting on the object, which is the friction, which main task is actually to reduce the speed to slow down the object. Okay, so in your answer, you have to tell the markers that there is a force or there is still friction acting on the object. And what does it do? And what does it do? It actually reduces the speed. Okay, remember to tell the marker it has to reduce. It doesn't stop immediately. Okay, because just now you're actually moving. So now with the force applied, the friction applied, without the applied force, the objects actually will first slow down, then he will stop eventually. So you remember the sequence, okay? The story here we are looking at is not like those you see on this cartoon whereby it stops immediately. Things don't stop immediately. There will be a split second whereby the object need to slow down before it hit a stop, before it hits 0 meter per second. Okay, so look for the information, look at how the question is structured, look at how the clue is hidden in the passage. Okay, that's what I would say that this is more important than the answer. It's the thinking process and the way you dissect the question that is more important. Because if you just remember the answer, you can only answer this question. But if you understand how it works, if you understand how to think, what to think, where to think, then you will be able to decipher other questions that come your way easily. Okay, so the same thing for this question 14. You have a roller coaster question. Okay, roller coaster questions, one of the things that I always highlight to students is actually to be careful of the height. Okay, because the height actually has some hidden meaning behind it, meaning there will be energy, certain energy that is available at that particular height. Okay, so you will be given for the question, you will be given a motor that's power rating of 100 kilowatt. Take note, 100 kilowatt, it means 100 kilo means 1,000. Okay, so it will be 100,000 watts. Okay, so take note of the prefixes. Okay, and the object and the train carriage and the object is 3,000 kg. So now, before we do, okay, since we know that this is a conservation of energy, one of the good practice I have encouraged students to adopt is that before you start solving, write down all the energy or identify all the energy that's available at each point. Okay, because in case you need to use them later on, so you will not be blur or confused or left out. Okay, so for example, for point B, based on object, the carriage actually reach the top and it stay there for a while. So at point B, the energy available is actually only potential energy. Okay, then after that, the carriage will actually dive down all the way down to point C. At point C, remember, point C is not the lowest. There's a height of 6.5 meters above ground, which means that there is actually a potential energy at this stage, point, okay, due to a 6.5 meter. And at the same time, the carriage is coming down all the way down. At this instant, at point C, there will also be kinetic energy. Okay. Likewise, if you go for point D Point D will also have the same thing. Point D will also experience the same thing, whereby you also have a particular potential energy, right, due to the height given here. And you also have, you have potential energy due to the height. And similarly, if no other information is given, maybe we can just assume the roller coaster just carry on. So you will have actually a certain kinetic energy at point D. Okay, so these are the energy allocation for each of the location here. Okay, so I always have this habit of identifying all the energy first, okay, before I start to solve the question. Okay, so now same thing, state energy conservation, principle of conservation. I would just say, just do your homework. Okay, after that, just get your 2 marks. Okay, it's quite straightforward. Okay, conversion of energy from A to B. A to B is here. Okay, given based on the question, okay, at point A, the only thing that is doing work is actually by the motor and by the electrical motor. So in fact, whatever we are looking at is actually the electrical motor pulling the object up. So I will safely say that the energy that I'm looking at point A is actually electrical energy. Okay, the electrical energy is running, is converting the work done to pull up the carriage up to point B. And eventually, when he reaches point B, get at the highest point B, the only energy that is available at point B, it will be actually your potential energy. Okay, and that's how I know what is the conversions that's happening at different part of the question. Okay, by identifying them first, looking at the questions to see what energy is available. Now at point C, calculate the potential energy at point A to B is a straightforward thing, mgh. Okay, things to take note. Height given for point B is 72 meters, of course. Okay, stay in the question. Take note of the common traps. Make sure you don't fall for the booby trap. Mass has to be in kg. Okay, in this case, of course, 3000 is in kg. Okay, G is gravitational field strength. Okay, which is always 10 Newton per kg. So make sure all the factors that you substitute in, all the values you substitute in are actually in SI units. And once they are in, press your calculator, you get the answer actually in joules. Okay, remember to write the energy. Now, time taken for the carriage to move from A to B. Now, from A to B here, right, this particular section here is actually done by the motor, okay, which is your 100 kilowatts. Okay, so remember the other formula that involve time, power, and energy is actually your power formula, energy divided by time. So if you know that the power is 100,000 watts, the energy given is in question in the front, part C, which is 216, 1, 2, 3, 4 joules, okay? You will be able to find the time taken. Okay, so by do a simple algebra manipulation, okay, you'll be able to get the time to be 21.6 seconds. Okay, easily done. Okay, but first cut, remember the formula. Okay, now in reality, it actually takes B a longer time, okay, to get to the surface. Of course. Why? Okay, it could be maybe like you could factor in like some common thing based on this question. The question never include a few things. The question never factor in like maybe air resistance. Okay, it could be air resistance, okay, that's present on that day, because 72 meters is very high above the ground, so there will definitely be wind. Okay, so there will be energy needed to overcome the air resistance. So I would say it's energy needed, okay, to overcome the air resistance. Okay, so this will definitely take out some of the energy that's generated by the motor, by the power, by the electric motor. And similarly, there might be friction along the track, which also was zap up some of the energy generated by the motor. And end of the day, with some of the energy being diverted to all these losses, okay, the energy that's used to actually increase the height of the object, the carriage and the passenger, okay, will be lower. And as a result, it will take more time, okay, to actually transfer the carriage up to point B. Okay, now, ideally, okay, in ideal case, okay, where everything is exactly the same, you'll find that energy is conserved. And part C, okay, I will need to find the speed of the point, at point part C. And the easiest approach is to use energy. Okay, because I actually would know what is the energy available at part C, point C, and wait, give me a minute. What color did I use? I think it's green color, right? Yeah, it's green color. Okay, so I actually know the energy that's available at part C, and I also know the energy that's available at part B. And conservation of energy is obeyed, both energy must remain the same. Okay, so energy at point B, I listed out in the beginning. There's actually one energy at point B, which is potential energy. At point C, there are two energy here. Okay, so what I do, okay, let me list down the working. So at point C, there's actually two energy here, which is EK and EP. At point B, there's actually potential energy at point B. Okay, so what I need to do is I need to figure out what is EK first. Okay, so let me give this P in case we get confused. So this C. So what do I do? Let me shift the working over first. Okay, let me shift the working here. Easier to see. Okay, so once you are here, so what do you do? Okay, I'll rearrange. So I get EK equal to EP potential energy at B minus potential energy at C. Okay, and this is what I'm actually doing. Okay, in a nutshell, what I'm doing is actually looking at how the energy is conserved, because when the carriage actually dive down to point C, okay, he actually loses this amount of potential energy. Gravitational potential energy. If I'm not wrong, it's 65.5 meter worth of potential energy. Sorry. So this amount of energy is actually converted to the kinetic energy of the carriage at point C. Okay, which is why I'm able to work out the kinetic energy at point C. Okay, once I have the kinetic energy, I will just revert to the basic formula for kinetic energy, half mv squared, and rearrange the formula. I should be able to find the velocity of the carriage at point C. Okay, the important thing about this approach is that students must know that the conservation of energy at B and C is conserved, and the students must be able to work out that at point C, okay, the energy actually consists of two energy, which is your EK and EP. Okay, one of the common mistakes that I see so far is that students always just equate the energy at B potential just 100% equal to the kinetic energy at C. Okay, totally ignoring the potential energy gain, the potential energy, the existing or the remaining potential energy at C, which is due to your 6.5 meter. Okay, so please take note of the question, how the question is crafted, and I would say answer the question accordingly. Okay, don't just make your assumption, because previous questions most questions you always see that the kinetic energy always equal to potential energy. Okay, but it doesn't mean all the questions has to be done that way. Okay, so please take note of it. Now, for part G, okay. Now, a simple thing whereby energy is for conservation of energy, students, you have to take note that for conservation energy, in ideal cases, okay, mass is actually not a big factor, because conservation energy, the mass actually will be cancelled out. Okay, in the sense that the mass will be a common factor on both sides, before and after. So because it is a common factor for both sides, it is actually not a deciding factor. It's not a dependent factor that will affect the energy. For example, if you look at it in terms of mass, okay, if I have potential energy equal to the kinetic energy, okay, for example, ideal case, mgh equal to half mv squared. Okay, you'll find that because both sides, before and after, okay, this is before, this is after. Okay, you'll find that mass is a common factor for both of them. And because it's a common factor that remains the same throughout, it is a factor that is independent of the energy. Okay, so because it remains the same before and after, mass is not a factor that will affect the energy. And because of that, okay, no matter how heavy my carriage is, in ideal case, in ideal case, no matter how heavy the object is, because mass remains the same throughout the motion before and after, mass actually will not affect the velocity of the energy of the object at that particular locations. Okay, you can also reason it that way in the sense that if I want to gain this amount of potential energy, if I have a heavier object, I need to exert like more energy to bring it up. But because it's heavier, when I move it down, okay, when it gathers speed, it also need more energy to attain the speed that is required. And because of whatever I gain and whatever I use at it before and after, the mass, the change in mass actually doesn't affect the speed that I can attain. Okay, because mass is a common factor, and because of it's a common factor before and after, it actually doesn't affect the speed of the object here. Okay, now if you are still not sure, if you're still confused about this particular section, okay, just pause the video and just scroll back a bit, rewind a bit, and just watch through again. If you still have problem, okay, feel free to leave a comment or email me the question so that I can actually address it in detail. Okay, now for the last question, question 15, okay, it's a circuit question. The calculations, okay, students, you need to be very sure of your calculation because circuit, the main part of circuit at O level is actually calculation. So you have to be very sure about your calculations, okay? Now, for this particular question here, we are looking at 2 amp current. The current is 2 ampere at 3 ohm. Okay, so this is 3 ohm and 6 ohm, they are in parallel. Okay, so the first thing we are looking at is that the current, because they are parallel, okay, you'll find that the current at, give me a minute, sorry. Okay, so the things to take note for parallel circuit, remember, we are looking at the 2 parallel circuit, 3 ohm and 6 ohm. Okay, so one of the important things that we have for parallel circuits, remember the potential difference, the potential difference between these 2 branches. Okay, because they are parallel branch, V3 and V6, okay, they are actually the same because they are parallel. For parallel branches, remember, for parallel branches, the potential difference across them is actually the same. These are some of the properties that you have for parallel branch. For circuit, one of the important advice I give to students is do not attempt the question straight away. Look at the question first. Look at the questions. Appreciate the circuit first. Look at the circuit. See what are the common things, or what are the common factors, or what are the equations, or what are the factors that is the circuit is trying to tell you. For example, based on this circuit, I analyze 3 ohm and 6 ohm. I'm able to uncover that V3 potential at 3, potential difference across 3 ohm is actually the same as potential difference across 6 ohm. Another information I can decipher out is actually the current. Okay, based on the question, because it's parallel branch, I will know that I2, I3, okay, the eventually will meet up and join to become, I2 and I1, okay, eventually they will join, okay, to meet up with I3, which means effectively I'm saying that I3 actually consists of I2 and I1. Okay, that's what some information that I can actually decipher. And other factors I can actually get out from is actually I can find, if I want to find V3, potential difference across 3, I can use a simply Ohm's law, V equal to IR. If I want V3, I will need current 3, I will need the resistor of 3. If I want to find potential difference of 4 ohm, okay, same thing, I will use Ohm's law, VIR. If I want to find the potential difference across 4 ohm, I will need the current across 4 ohm resistor, and I will need the resistance across 4 ohm. And similarly for V2, V1, and what am I saying? V4, 3 and V6. Yes, V6 will be I6. Give me a minute. So if I want the potential difference across the 6 ohm, I will need the current across 6 ohm and the resistance of 6 ohm. Okay, so this is what I mean by you appreciate the circuit first. From there, you see what are the equations or what are the meaning or what are the factors that the circuit is trying to tell you before you solve the question. Okay, now let's go. Now, once you have this, you can go ahead and solve the question already. When you are ready to solve the question. So now the potential difference across the 6 ohm resistor. If I want the 6 ohm, straight away I know if I want 6 ohm resistor, I can either use this formula or actually I can use this. Okay. If I want to use V3, right, I will need this equation. So the highlighted in yellow one are the possible equation that I can use. And from here, all I need to do is decide which of the equation is the easiest or which of the equation has the most variable given. So I will just use it straight away. Okay, you'll find that I will not want to use V6 equal to I6 times R6. I will not want to use this because I do not know what is the resistor across the current here. Okay, which is R2. Let me erase first. Sorry about the labeling. Okay, so this will be I1. Okay, this will be I3 and this will be I2. Okay, I will not want, if I want to use V6, if I want to find the potential difference across 6 ohm, V6, I will not want to use this equation. But in this equation, I actually do not know what is I2. So it may not be the most straightforward equation to use. But then I will be able to use this equation, V6 equal to V3. Why? Because at V3, I actually know what is I1, which is given in the question. And I also know what is the value, what's the resistance for R3, resistor 3. So this is given to me, so I will just use straight away, I will just use this formula and my answer will appear straight away. Okay, this is what I mean by spend like maybe a minute, okay, in reading the question to appreciate the circuit, to see out what are the possible equations. And actually, that 1 minute that you spend reading the questions, deciphering the equation will actually make subsequent working actually much easier. And similarly, what's the value of I2? Okay, same thing for I2. Okay, I2, same thing. If I want to find I2, I can actually use this equation straight away. Yeah, because now I actually got V6 already. I have V6, I have V6, I have R6. Okay, which is your 6 ohm. So I can find the I2 straight away. Okay, so if you look at how I do it, it seems easy. Okay, partly also because I have done this a lot of times already. But one of the main reasons I have is actually I spend that 1 minute, okay, to read the question, to read the equations, to read the circuit, to identify what are the equations, what are the factors that is useful for me, which is, I think, is one of the important things that students should actually adopt. Now, for part C, okay, potential difference across 4 ohm. Now, 4 ohm here, okay, 4 ohm V3. The easiest V4 here, which I given here, sorry, V4. So V4, the easiest one is to use V4 straight away, the formula I3 times R4. Okay, R4 given is 4 ohm. I3, do I know I3? Yes, I know. I3 is here, which is a sum of I2 and I1, and which I have already. I have I2 and I work out I1. I work out I2 and I have I1. So I will just work out I2 plus I1. This is I2 plus I1. Multiply the resistance, which is 4 ohm. I'll get answer straight away. Okay, it's quite easy. Okay, but the thinking process must be there. Okay, it looks easy, but the thinking behind is actually you need to practice. Okay, for students. Effective resistance across X and Y is a straightforward. Is a across X and Y. Across X and Y, remember X and Y. X and Y is the whole branch here, which consists of one parallel circuit plus a series in series with this 4 ohm. Okay, so parallel branch is series with your 4 ohms. Common mistake is your presentation. Now remember how you present your answer here. 1 over R equal to half. Then after, remember you must flip, okay, the equations. Okay, remember you are looking for R parallel. Okay, the mathematics, please take note, present your answer correctly. Very common, I have this presentation where students like to write R parallel equal to 1 over 3 plus 1 over 6, which is equal to half, and half equal to 2. Okay, this math looks correct, but actually it's wrong. The idea behind this mathematical presentation is weird. Okay, because you are telling me that 1/3 plus 1/6 is half, and somehow miraculously half is equal to 2. Okay, what logic is that, man? Okay, it's like 50, I give you a 50 cent, then that 50 cent is worth $2 now. Okay, what is there's no logic behind it. Okay, so take note of the presentation. The wrong presentation, okay, will give the wrong meaning to the marker, and it will make your answer, it will render your answer useless, even though the answer is exactly the same as mine. Okay, so please take note of your presentation. And lastly, okay, XY is always, the reason XY is always higher. This one, most students have no problem with it. Okay, they actually know that it's, in real life, the wires are not ideal. There are definitely resistance in it. And this additional resistance cause the whole circuit, or will introduce additional resistance. And it will make the whole entire circuit, the resistance to be higher than 6. Okay, and as a result, okay, the circuit will not be like what you calculated, 6 ohm. In reality, it's actually more than that. Part F, state the value of how I3 will change. Okay, if the 3 ohm is replaced by a piece of wire. Okay, now take note of this. Okay, 3 ohm is replaced by a wire. Okay, the question asking for how I3 will change. So now if I replace this with a wire, I connect this with a piece of wire. Okay, let me connect this with a piece of wire, maybe a big one. Okay, I connect this with a piece of wire. Okay, now when I connect this with a piece of wire, okay, you need to take note that this is a piece of wire, ideal wire, the resistance is actually 0 for this piece of wire. Okay, so in fact, okay, first thing you know that you need to take note is ideal wire, the resistance is 0. At this point in time, okay, take note, okay, I have replaced 3 ohm already. And because this is ideal wire, it's actually caused a short circuit at this particular branch. And this short circuit actually has an effect. Other than replacing 3 ohm, other than removing 3 ohm from the circuit, because of this wire, it causes a short circuit. You will find that the current, when it comes to the branch here, the current will not go down to 6 ohm. There will not be any I2 now, because the above branch, the top branch now is 0 ohm. All the current actually will go up and will travel in the upper branch. All the current will travel up and you'll go through your 4 ohms, okay, bypassing your 6 ohm directly. So when the question says that I am actually replacing the 3 ohm resistor, I'm removing the 3 ohm resistor, the underlying clue that they're giving you is that they are actually also removing the 6 ohm resistor, okay, because of the short circuit incident. So once there's a short circuit, the 6 ohm is also being removed. So effectively between X and Y, because of this wire, between X and Y now, there's only a resistor now, which is 4 ohm. Okay, so this is what the question is trying to tell you. So in fact, from just now, okay, your resistor actually changes from 6 ohm. Just now the RT was 6 ohm. Oh, sorry. The total resistance was 6 ohm. Okay, and now it has changed to a total resistance of only 4 ohm because of the short circuit, because of the wire. Okay, that's what the question is trying to tell you or trying to hint to you. Okay, other than removing the 3 ohm, I'm actually removing the 6 ohm because of short circuit. And because I remove the 2 resistor, you'll find that my total resistor now actually decreases. And because my resistor decreases, the current through the branch actually increases. Okay, why? Because resistor and current has an inverse relationship. Lower the resistor, higher the current. Okay, so take note of the clues that is given to you. Okay, and take note of the meaning behind each of the clue. Okay, so students, for this paper, I will not say the paper is difficult. I would say it's like slightly above average. But importantly, like I want to emphasize that in solving the question, sometimes the answer is actually not so important. The more important thing is about the thinking process, is how you think. For the questions, from the questions, how do you identify the clues that's given to you? Once you have the clue, what are you going to do with it? What does the clue give you? What are the additional information that the clue actually give you? Okay, and that thinking process is actually more important than actually finding the working out the final solutions. Okay, it's the thinking process that I want to highlight to students. Okay, it might look easy when I do it or when your friend do it. Okay, but when you actually do it yourself, you might encounter some difficulty because it could be like lack of practice, or it could be like you are not looking at the clue correctly, or you're missing out certain clues. Okay, so it's important to actually get yourself familiarized with the concept and the clues that's given in the questions. Okay, if you have, like if you are not sure what are the clues, what are common clues or what are possible clues that can be in the questions, okay, you can actually take out questions and actually try to identify them. After that, if you need to, you can actually show your teachers, or you can just email to me, or you can just drop me a comment and let me take a look to see whether have you identified the correct clues, or have you identified all the clues for the questions. Okay, with that, I hope it actually helps you with your paper. Okay, same thing I like to emphasize again. Okay, if you need the paper, is in the link in my description. Okay, down you can just go to my Google Drive and download and just give it a try. Don't just look at the answer first. Okay, try it first. Okay, same thing. Okay, to get the alert for other paper that I going to upload. Okay, remember to subscribe and click the bell button. Okay, so that you get any emails or alerts whenever I upload some videos about papers or even new topics. Okay, if not, I would say that's all, folks. Bye bye.